thank you everybody for coming down tonight. I understand it's a Friday evening, so it's an absolute pleasure to be at King's College London. Well done for making the effort to come down on a Friday evening. It's very much appreciated. So I am here to talk about asteroid mining, as I'm sure you can probably tell. I'm Mitch Hunter-Scullion, I'm the CEO and founder of Asteroid Mining Corporation. So I actually founded my company in my university bedroom 6 years ago now. So I was once an undergraduate with a big idea and a dream, and here I am today. So I would like to talk you through that journey over the next kind of 30-45 minutes, and then kind of work to engage with you as to how you can get involved not only in the space resources industry but just more generally in space entrepreneurship. So, asteroid mining. What is asteroid mining for a start? I think we should really kind of break this down and conceptualise what it is that we're actually doing here. So, asteroid mining is the prospecting, exploration and extraction of resources from asteroids at its simplest. So use cases for asteroidal material, let's kind of break that down. Platinum group metals in particular are what we're interested in. The reason for that being that platinum is currently kind of about £25 million a tonne, give or take, and on Earth we currently mine about 200 tonnes a year. So the total market capacity of platinum mining is about £4 billion per year. And I would quite strongly argue that even half of that amount of money would lead to an enormous increase in the amount of platinum in the global supply, as I shall come to in the next short while. So platinum group metals have myriad use cases: hydrogen fuel cells, catalytic converters, electronic devices, turbine blades, medical equipment, and many other products on Earth. Also, I suppose, if we're talking about asteroid mining, it's really important to not just focus on platinum, because platinum is the initial economic incentive, but when there is an initial economic incentive, you can find a pioneering use case in an interest, that is platinum. But beyond that, asteroid mining means the utilisation of space resources more generally. So a generalised utilisation of space resources means that things like water extraction from asteroids becomes economically viable. Beyond water extraction, things like, I suppose even just with water extraction, you can split water or waterise from asteroids into hydrogen and oxygen. You have rocket fuel, you also have, beyond rocket fuel, kind of life support systems, or life support for astronauts. So there's an emerging use case for various asteroids, but I'll break that down in a minute and just kind of give you a small bit of background on AMC in a minute. AMC was founded to develop the enabling technology for the global market in space resources. Asteroid mining is a very small part of what is an emerging industry, and that is the global space resources industry, of which the global space resources industry is predicted to become incredibly valuable in the next 10 years. And when I say incredibly valuable, I'm talking about considerably more valuable than almost any other industry that came before it, as we shall get to in a minute. But in order to get to the stage where asteroids are particularly valuable and are providing the economic incentive for space resources or space exploration that we're all looking for, I think there has to be some development work done in the meantime. And I would like to think that the technology that we're currently developing is how essentially space resource utilisation will be funded. And as we like to say, consider us the shovel salesman of the 21st century gold rush. It's a lot of money to be making asteroids, it's a lot of money in space resources at the minute. It's actually quite scandalous. The sky is not the limit. So, there are millions of asteroids in our solar system. Millions. There is at least 4 million asteroids in the main belt. We know of at least 19,000 asteroids in the near-Earth asteroid belt. So if you look on the right there, you can see 28,000 counted to date. In fact, my figures are slightly outdated. But you can see an animation showing that there is a lot of asteroids. Particularly in the near-Earth belt, there's enough asteroids to sustain human development, human civilization development for centuries to come without having to go beyond to the main belt. We find ourselves blessed with the early remnants of the solar system, essentially standing there, ready to be, accessed. They're not very far away. In fact, if you can see in that animation, probably the majority or so are within Earth and Mars, so it's not a very long distance goal. They're accessible, quite quick to get to for the most part as well. And by getting to these asteroids, the amount of value that one could potentially extract is just phenomenal. So let's move on to that. The economic potential of an asteroid. This is just one singular 1 kilometre diameter, upper 90th percentile, bountiful platinum-bearing metallic asteroid. Let's give you some jargon there. But with your 1 kilometre diameter metallic asteroid, the upper 90th percentile, you can reasonably expect to find £20.19 trillion worth of resources. That's just platinum group metals and gold at the current market valuation. So 20 trillion, give or take, is roughly equivalent to 8 times the gross domestic product of the United Kingdom, and that is one asteroid. One asteroid, and that is considerably, not even a very exciting asteroid. There are much, much more valuable, much bigger asteroids out there. This is just one that's relatively close to Earth. So to break that down, platinum group metals is obviously what we're looking for because of the highest initial return when it comes to what you are ultimately aiming for. And just to kind of look at platinum here. So the annual global production of platinum last year was 170 tonnes. In fact, since I prepared this slide a couple of years ago, that's actually went down. So I think this slide is probably about 2-3 years old now. And 3 years ago, when we prepared this slide, it was 195 tonnes of platinum. So we were actually decreasing in platinum output on a year-by-year basis. But the demand for platinum is not decreasing proportionally. The demand for platinum is essentially accelerating. And the reason for that being that platinum group metals are so fundamental to our global technological society. I'm sure almost everyone in here has a smartphone. Smartphone production takes 25% of the global platinum supply immediately. So there's about £1 billion worth of platinum goes into smartphone production every single year. And that's just for tiny trace amounts of platinum inside your phones. And that's before we even start to look at future applications of platinum group metals. So things like, the hydrogen economy, catalytic converters, whatever. So to go slightly more into detail, beyond platinum, because platinum is just one part of ultimately quite an exciting economic opportunity, I would argue that palladium is in fact the most exciting thing that we can be looking at the minute, because compared to the annual global production and what we believe that we can provide from an asteroid, then palladium would suggest itself to be one of the most valuable resources in the solar system. Looking at that slightly more as well, things like iridium, there is just an enormous amount of value in iridium and rhodium. These platinum group metals are so scarce on Earth because for the most part you find them in impact craters from previous asteroidal impacts onto Earth. So if you look at kind of the Bushveld complex in South Africa, it's an impact crater. These are predominantly seeded from solar system impacts with Earth, and the reason for that being that in the early formation of the Earth and the early formation of the solar system, the platinum group metals are some of the densest elements, so they inevitably tend to sink into the crust of the Earth. So they become difficult to access, but through that difficulty presents opportunity, and I'm a filthy capitalist, so opportunity is what I look for. And I do believe that, considering that a single 1 kilometre diameter asteroid could potentially be worth £20 trillion, there's a big enough economic opportunity to go and start looking seriously at these resources now. So let's look at the long-term view of space resources. So global resource competition is increasingly driven by demand for non-fuel minerals required by emerging technologies, whose supply is unevenly distributed across the globe. Some of you may have heard of Elon Musk's "We will coup whoever we want." Is a very good example of why kind of resource independence is incredibly important in the modern day, because we cannot guarantee supply of resources at this point, particularly platinum group metals. In the UK, we do not have a platinum group metal capability, and it does not exist. We cannot dig up a big hole in Yorkshire and say, oh, well, we can find 200 tonnes of platinum there annually. It's a very limited resource and it's very limited global supply. So, considering that the global economy is dependent on this resource, we find ourselves in a scenario where there is a requirement for nations intending to stay at the cutting edge of innovation to source a steady supply of strategic resources for their industries. Talking about the hydrogen economy, for example. The hydrogen economy requires platinum group metals. Next generation engines require platinum group metals for ultra high temperature superalloys. These are necessary elements for the future of the global economy, and at the minute these elements are predominantly supplied from countries which do not have the best relations with the United Kingdom, we shall say. So as we look to expand our supply chains into the future, as we look to accelerate global development, we must look for new supplies of resources. This is a very raison d'etre of everything we do, because at the minute, looking for resources has led us to mining the deep sea. I don't know if anybody here knows anything about deep sea mining, but I will happily go on record as saying that this is perhaps the most environmentally catastrophic thing that I can possibly imagine. And one of the things that we get accused of very regularly is, well, what if there is an alien on an asteroid? What if you're destroying an ecosystem that you don't know about? And my response to that would be that we are already destroying an ecosystem that we do not know about. We are more than happy to mine deep sea floor in the Pacific, and there is 400,000 square kilometres of the Pacific seafloor which is currently being mined, at least. We know there is things alive in the bottom of the sea. We speculate that there might be something alive on an asteroid, and I would argue that it's dead rock. My default position when it comes to asteroids is that these are inert, dead rocks, nothing living on them. These are just, the early building blocks of the solar system, and as a result, have absolutely no environmental benefits. Obviously, it would be foolish not to do a full scientific review of these places, of these locations, before obviously you conduct mining operations, which will be ultimately somewhat destructive. But when we're already destroying the deep sea floor, and we are ultimately aiming to go and mine dead rock in space, I would like to present asteroid mining as being the ethical and environmental alternative to that. And I suppose it really does come down to the use cases for platinum as well, because platinum and platinum group metals is one of the most valuable materials that we can currently mine on this planet. But it needn't be that way. Platinum is scarce on Earth, but that is ultimately, in a solar system level, quite an artificial scarcity. There is a lot of resources in our solar system, and currently we are not accessing them. The benefits to our technological society that we could gain by mining even one small asteroid would radically alter the global economy and would allow us to transition to a greener and more prosperous and more sustainable future. And even as spin-out applications, there is the example of the hand there. Platinum is fully biocompatible, so biotech applications, I don't know if any of you are biologists, but biotech is one of the applications that you could be using platinum for as well. It's not purely energy, it is a very, very versatile element which we do not have much access to. So, if we're looking at a green transition, obviously I'm not sure if you can tell, but I'm from Glasgow, and COP26 was in my home city very recently. So, the transition to a greener and more sustainable future is very much at the forefront of everything that we like to do. And the UN Sustainable Development Goals are very much something that we're aiming towards supporting and developing further, because the Sustainable Development Goals only go to 2030. We can go further than that, 2030. I'll only be, 35 by 2030. Most of you will still be in your 20s, I imagine. So that's not very far away. It's not far away at all. And if that is the end goal of where we're aiming for, then that's just kind of short-sighted, I would argue. We can go considerably further than 2030. We can go to 2040, 2050, 2060, 2070, and still expect to kind of be hanging around and, you know, be developing industries and things like that. So the high cost of platinum group metals is inhibiting the green energy transition. And if I can allow you to take one thing away from this talk tonight, I would like it to be that. Platinum group metals are artificially high in cost because Earth does not produce enough. But the solar system does. The solar system is abundant in platinum group metals. We do not have to suffer through this shortage, this scarcity. We can progress to a much more sustainable future. And as part of that, I think hydrogen fuel cells are one of the key technologies acquired. And one of the main problems that I've foreseen with hydrogen fuel cells would be that in order to have a hydrogen car, for example, you need a kilogram of platinum. A kilogram of platinum currently costs £25,000. So for one component in one engine in a hydrogen vehicle is £25,000 before you build the car around that component. I mean, it is the key component, but it is ultimately just one singular component in that vehicle. So if you can ultimately bring the cost down of platinum, and as we've seen, jump back to, you can bring the cost down of platinum, like just in that upper 90th percentile 1 kilometre diameter, like metallic asteroid, there will be 117,000 tonnes of platinum. So considering we mine 170 tonnes a year, it's 1,000 times increase in supply from a single asteroid. And that asteroid, once you develop the infrastructure, it's just going to stay there. It's going to become the most productive mine in human history. So it's very important for the development of, you know, the green transition to start thinking about space mining, because the alternative is the green transition is happening completely independent of the space resources industry. This is something which ultimately will happen regardless, but if it isn't handled in a delicate manner, then we're going to find ourselves in a position where we will absolutely destroy the deep sea bed in order to find, you know, platinum group nodules on the seafloor. And I just don't think that that is in line with the Sustainable Development Goals. Sustainable development requires sustainable development, and I can't help but think that if you're mining the deep seabed, you're not developing sustainably. You are ultimately just proliferating a cycle of destruction, which our planet could really do with avoiding at this point. But fortunately, asteroids are dead rocks, so there's nothing out there. And to be honest, if we do find something in an asteroid that is alive, then I will almost certainly win a Nobel Prize. So don't mind either way. It could be worse. It could be worse in either direction. But our default position is that it's already dead. There's nothing there. There was never anything there. There's been no life on an asteroid ever, as far as we're aware. So why are we more restricted to go to space than to mine on Earth, is the question that I would like to pose. There is currently more international oversight, more scrutiny, more committees, more discussion about space resources than deep sea resources. And I can't help but find that to be a bit of a kind of, you know, a mauvaise foi, a bad faith exercise, because we know one is dead and we know one is full of life, and we are mining the one which is full of life, and we are killing things on the deep sea floor, whereas the one which is, you know, inert, dead rocks floating in a vacuum, hundreds of thousands, if not millions of miles away from anything else, is the one which is currently politically difficult to go and mine. And I can't help but think that's a bit of a backwards viewpoint, especially considering the vast economic value of a single asteroid. So, metals extraction predominantly takes place in the global south as well, and there is a very strong ethical position to be taken here, in that when you're looking at metals extraction, there's a phrase, and I genuinely think it to be one of the most horrid phrases I've ever heard in my life, but artisanal mining. Does anybody know what that is? Artisanal mining is where you essentially have kind of very low paid labourers who are responsible for their own very small mines, and the Global South who's ultimately take the kind of the difficulties involved in mining onto their own backs. So they are not organised by a kind of an overarching corporation. They provide their mined materials to a supply company who then introduces that to global supply. And that is just like astonishingly difficult for, you know, both an ethical perspective and an environmental perspective, because when you have artisanal mining, you do not have environmental controls. You have ultimately a free-for-all, and how low can you go? How low can you go on ethical standards? How low can you go on environmental standards? And just labour relations as well. Like, you're talking about some of the poorest people in global society who are being made to go and mine in the worst environmental conditions. And I would like to argue that this is unnecessary, and that ultimately it is not our intention to put these people out of a job. It is our intention to help support the transition away from unethical mining practices in order to support a more bright and sustainable future. So, for example, marine and terrestrial solutions to increase mining supply are counterproductive. We cannot realistically be expecting to mine the deep sea floor forever without expecting to have a mass extinction level event on, you know, whatever's at the deep sea. We don't even really know what's in the deep sea for the most part. Like, if you remember MH370, the statistic that I found astonishing was that we just don't actually know. Like, we don't have accurate maps of the deep sea beds. We have some maps, and for the most part they're fine, but we have more accurate maps of the surface of Mars than we do of the surface of the deep sea bed. And that's astonishing. And considering that, you know, no one is currently suggesting to mine Mars, or possibly Elon Musk has got Emperor routine, but no one is seriously suggesting to mine the surface of Mars because it's economically viable. But mining the surface of our planet, even, you know, deep sea surface, is currently happening, and it is happening right now. There are companies on this planet who are destroying the seabed, and they are making money by doing it. They are perpetuating a cycle of inequality, because the money which stays in the deep sea bed mining industry is going to shareholders, it's going to investors, it's going to, you know, stakeholders ultimately. It is not going predominantly to the people who are ultimately licensing this exercise. So when it comes to space mining, there is kind of two main fronts that I would argue here. One, you must be licensed by a national government. In order to do anything in space, you require kind of national oversight, national kind of you know, just investigations into what you're doing. You need to demonstrate technical capacity, really demonstrate that you have the capabilities to do what you're setting out to do. And for the most part, I think that the space industry is very good at doing that. I think the space industry is very accountable, and going forward into, you know, the 2020s and 2030s, when it comes to space resources, we're only going to get more accountable. Transparency and accountability are two of the main watchwords for the space resources industry, compared to what we currently find, where we have lovely euphemisms like artisanal mining, deep sea mining, and don't really account for the environmental and ethical destruction that this entails. But even with things like low externality resource acquisition, we must, if we're going to progress towards sustainable development, have these resources. It is just a mere matter of fact at this point if we're going to progress towards the green transition that we're aiming for. So space-based platinum group metals would have an order of magnitude less CO2 equivalent per kilogram than those extracted from platinum group metals, because they take place outside the atmosphere. Once you have launched your rocket with your mining rig, it's out the atmosphere. There's no environmental damage at all. There's no terrestrial environmental damage at all. There's still environmental damage, of course. Mining is a damaging industry. That's unavoidable. No one is arguing against that. However, would you rather that environmental damage happens on Earth where we know there is a biosphere which contains an enormous amount of life, an enormous amount of, hopes, dreams, fears, whatever? Or would you rather that environmental damage happens 4 million miles away, where there is nothing, there is some rock that we can go and find in a vacuum? So I would very much argue that space resources is the ethical alternative. But to break that down, what is it that we do at Asteroid Mining Corporation is that we are a space exploration company with the long-term goal of the utilisation of space resources. So I actually had the great honour of announcing this publicly for the first time. Thank you, Casey, for giving me the platform to do so. But we have just signed and paid for a partnership with Tohoku University Space Robotics Laboratories in Sendai, Japan, and we are currently developing space-capable asteroid robotic explorers, which are hexaped climbing robots with use cases on Earth, as well as delivering, and as you can see it's in yellow, the last mile logistics in space, we like to call it, because you have rockets, and rockets can get you to the moon. But once you land at the moon, what do you do? If you have a lander, you go no further. You've spent all that money to get to the moon, and then you have a lander, and then that's it. If you look at the Curiosity rover, for example, on Mars, it's quite far. It's very exciting, but it's got wheels. So what we're developing is legged robots. And I would argue that legs will always beat wheels in a space application, because when you have wheels, you are dependent on gravity, whereas when you have legs, you can climb, you can scramble, you can go anywhere you want. So this ultimately leads to the idea that you can go anywhere and borderline do anything within the inner solar system with a legged robot compared to a wheeled robot, because it's that last mile. You can travel 250,000 miles to the moon, but it's when you get there is important. If you can travel 250,000 miles to the moon and then go no further, then I would consider that, for the most part, to be a wasted mission. I think that if you're going to spend all that money to go to the moon, you might as well do something when you get there. And I think the exploration of water ice and craters and anything like that is so important going forward. But our robotic platform SCARE is just ultimately the first step in what will ultimately become the space resources industry going forward. So SCARE has two applications. One, ostensibly, is for asteroid exploration, it's for lunar exploration, Martian exploration, whatever. But the unique capabilities of our robot will lead to commercialisation on Earth. And we're already in the process of doing this. So we're already starting to look at making money on Earth with space technology. And for the most part, the space resources industry does not make money. In fact, if anyone can turn around into a single profitable space resources business, as far as I'm aware, anywhere in human history. So that's our goal. We don't only want to go and mine space, and in order to get to that asteroid mine of 2030, 2033, you need to make money for the next 10, 12, 13, 14, 15 years. And that's where SCARE comes in. SCARE is part of our 20-year vision for enabling asteroid mining. And it begins initially with terrestrial robotics. So we actually started our project somewhat in stealth mode at the end of last year at Tohoku University. I'm very, very happy and fortunate to have them as partners as one of the world's leading space robotics research labs. So, space-capable asteroid robotic explorers are a multi-use robotics platform offering unique terrestrial capabilities. And when I say unique, these are six-legged spider robots which, in their final form, will be able to climb up there, and just under a one gravitational environment, they will not have any problems with climbing the walls and ceilings, just due to the unique IP and the gripping technology that we're currently developing. So we anticipate applications in things like industrial inspection, infrastructure inspection, because we need to pay our bills. And if you can't pay your bills, are you a proper company? Go and ask Planetary Resources, because they're not here anymore. So, no, you're not a proper company if you can't pay your bills, is my first major point in that respect. But once you can pay your bills, once you can sustain revenues for a long enough period, well, where do you go with that? Obviously, clues in the name, asteroid mining. If you can pay the bills, you can continue to work towards the end goal. And I'm in a very interesting position in that the first thing I did with this company was think of a name. I had no idea what else I was doing. I had a name and I had an idea, and that idea was asteroid mining. So everything else that's came since then has been to support that initial aim. But what we actually have done for the past, well, most of the past 6 years is actually working on what we now politely describe as phase 2, which is prospecting. So the Asteroid Prospecting Satellite series of missions, which will be ultimately space telescopes for the most part. We're doing a bit of ground-based work at the minute with the University of Plymouth, but we are ultimately aiming to use the ground-based capabilities to feed into the space-based capabilities. So it's a series of space telescope missions. Ultimately, Asteroid Prospecting Satellite 1 will be arguably the flagship of our industry going forward, because we intend to categorise 9,000 asteroids per year. And to put that into context, we have, as a planet, not just kind of as a space industry, as a planet, we have categorised about 1,500 asteroids in total. So in order to understand the compositions and ultimately the economic values of these objects, you must know what they're made of. You must kind of, you have to know what they're made of, because otherwise you cannot spend X amount of money to go and kind of investigate the resources. You have to be able to take that ground-based perspective, well, ground-based on one side and then space-based perspective, not just to identify resources. So that's the prospecting phase. But then going into phase 3, which is exploration, which is obviously quite far away now, we're at least 7 years away. But the Asteroid Exploration Probe series of missions will launch one of our space-capable asteroid robotic explorers on board a spacecraft to the selected mining candidates identified by the Asteroid Prospecting Satellite in order to explore the surface, take core samples, test mining technologies, and most importantly, stake a legal and internationally legitimate claim over those resources. Because at the minute there's some legal development that has to take place as well, and that's probably going to involve the UN at some point. So, allow me, for the first time publicly ever, to introduce you to space-capable asteroid robotic explorers. These are the robots that are currently being developed in Japan. So, the one on the far right, as you can see, is actually quite an old model. So that's from 2018, so that's 4 years old now, and it's only got 4 legs. But it could walk, it could climb, it could do various bits and pieces. But 6 legs are definitely better than 4, and someone going to Boston Dynamics that. So with a 6-legged robot, you have multiple points of contact. You have the capability to grasp and grab on to various structures in front of you, and have, with those multiple points of contact, I don't know if you can see with the little grippers on the end, but you have the capability to not only grasp on one leg, but with 6 other legs with multiple points of contact on the end effectors of each leg. You don't just have, one gripper, you have essentially 36 grippers which can all independently operate. And that's incredibly exciting from our perspective, because it leads to ultimately where we're going with this. In that we started the project 4 months ago, 5 months ago. We are aiming in the very near term, so next June we will be unveiling our functional prototype at the International Conference in Robotics and Automation in London. And then beyond that, we are looking to start producing these robots initially for terrestrial applications. And I think that's the real takeaway here. If you can't pay the bills, you're not a real business, you are a startup. But if you can pay your bills, you're a real business. So our initial aim is to produce 48 units of our robot per year from next year, at which point we can reasonably expect to have enough scaling revenue beyond that to ultimately support the development of the space resources industry going forward. And that is with ultimately one quite small robotic capability. And as you can probably see, it's scalable. So the robots that we are starting with will have about a 20 kilogram mass budget, because obviously space, don't want to be sending lots of extra weight up if you don't have to. The smaller, the lighter you can go, the better. But if you can ultimately expand that, and if you have the money to send bigger and better robots in the future, then you can look to start sending quite sizable robots. So we reasonably estimate that we can size up one of our robots to 200 kilograms and still have it kind of space capable. So with a 200 kilogram robot, I mean, if it's about 1.5 meters across at 20 kilograms, then a 200 kilogram robot is going to be enormous. And as I'm sure you can probably recognise at this point, this is probably where the scary name comes in. My Glaswegian accent probably helps that somewhat, but it's a scary robot. It's absolutely terrifying. I've seen these robots in the lab and they are intimidating. They are big, they have big claws, they're capable of climbing, and they are going to go many places. But before they go anywhere off our planet, they're going to make money here. And there's markets that we can already identify and that we're engaging with, and things like infrastructural inspection, which is oil and gas, nuclear industry, don't want to be sending humans. In fact, anywhere that you wouldn't want to be sending humans, send a robot. In particular, send a space robot, and then you don't have to worry about things in quite the same way. Extravehicular activity, so at the minute you send someone in the outside of the ISS in order to do visual inspections. Why not send a robot to do that at a fraction of the cost? Bridges, they're a great example. Search and rescue, disaster relief. So our robots have actually been tested in Fukushima, in Japan, which I'm sure you are probably all aware there was a nuclear accident there a few years ago. So it's a difficult environment to work with. So within that difficult environment, again, send a robot. Cinematography, why would you have someone climbing out the side of the tree or up a building when you can send a robot to do that and attach a camera to the side of it? Minesweeping, again, you don't really want to be sending humans into minefields. Put a human, put a robot, put a robot into a minefield, and then you can avoid human loss of life in what is ultimately quite a dangerous scenario. Forestry, there's quite a high death rate within the forest industry, even just in Scotland. It's your life expectancy goes down if you work in forestry. So again, send a robot, put a drill, put a saw on the side of a robot, and I suppose perhaps most excitingly, asteroidal and planetary exploration. You wouldn't want to send an astronaut to an asteroid because it costs too much and you have to keep them alive. Send a robot. So these are our partners at Tohoku University. So this is actually Professor Michael, it's clearly not been updated this slide. So that's Professor Michael, who's our Chief Robotic Engineer at Asteroid Mining Corporation and the Assistant Professor at the Space Robotics Lab, and Professor Kazuya Yoshida, who's widely regarded as the godfather of space robotics, ultimately anywhere in the world. So we are very fortunate to have a partnership with the Space Robotics Lab. They are as good as it gets when it comes to space robotics, and they have contributed previously to the Hayabusa 1 and Hayabusa 2 asteroid sample return probes. They were also participants in the Google Lunar X Prize as part of the Japanese team at Kuto. And their research goals ultimately lead to Earth terrain mobility and remote planetary exploration. So let's go into a bit more detail on scary, because it's quite an intimidating creature. So it's biomimetic, in which its design is inspired by reptiles, insects and arachnids for mobility in extreme environments. So the actual end effectors, the grippers that you can see there, are actually based upon geckos for the most part. So you're looking at kind of taking what you can from the reptile world, but as you can probably tell, it's got 6 legs, it kind of looks like a spider. It's predominantly based on arachnid biomimetics. But the problem with Scary compared to a spider is that we are actually modular. So it's a swappable payload for versatile mission profiles, which means that you can aim to do ultimately anything. So, for example, KCL, if ever KCL wanted to send something into space and test it in space, then there would be space on one of our robots for hosting mission platforms. Symmetrical reversible architectural for omnidirectional mobility. So, it can flip in every direction. There is no right way up in space. Your kind of centre of reference is quite skewed as soon as you get beyond our planet, because whatever way you want to say is up, according to your inner ear. So that also applies to robotics. The platform is scalable from 20 kilograms, and our initial prototype to 200 kilograms. We fully anticipate underwater microgravity and vacuum capabilities. In fact, obviously the last two are very much designed from the get-go, but the underwater capabilities are a very interesting opportunity going forward as well for things like subsurface infrastructure inspection. They are radiation hardened because obviously the space environment is highly radioactive, and they're toxin proof because robots don't get gassed. Robots don't have to worry about breathing. They just cut about, go through anyway, and don't really have to worry about anything like that. And the electronics are owned by ourselves, which is very exciting. So the terrain mobility is something that we're very excited about, in that there's an extremely uneven terrain on asteroids. Wheeled robots will not work on an asteroid. You just cannot. The gravitational environment does not support it. The terrain does not support it. Even on the moon, if you're looking at something like Shackleton Crater, if you have a wheeled robot, you can go in, but you'll never get out, and you'll get stuck there, because with a wheeled robot, you don't have the grip. You do not have the kind of tactile functionality in order to grasp onto what it is that you're aiming at. You have a very limited adhesion to the surface, and as a result of that, your locomotive capabilities are ultimately quite reduced. So, with a lead climbing platform, you can travel anywhere with a solid interface, including vertical and inverted surfaces. There's nothing really stopping a robot from going just about anywhere if it's got legs. And the grippers also provide tactile feedback, which I think is really important, because it allows you, say when I'm holding onto this desk, I can feel this desk, and I can kind of, in my internal logic, I know this desk is here and I don't need to worry about leaning against it. And you kind of want the robots to have that same kind of internal reasoning. So when it comes to internal reasoning, robot localization is obtained solely by cameras and depth sensing equipment. In space, there's no GPS. GPS is purely an earthbound thing. So in order to move, what you're seeing on the left there is actually the robotic eyes. So in the same way as I'm looking at you, I'm actually judging distance, and I'm seeing kind of, in the same way you can see that blue rock, I'm judging distance by kind of depth sensing in my kind of inner eye, and the robots work in a very similar method in that you can kind of judge distances, and as that distance gets closer, you get an understanding of how close you are to it, and it's essentially kind of, it's a heat map for the most part. You get a bit close and it gets turns red, you know you're too close. If any of you have a Roomba, it's very much the same technology. If you're hoovering in a robot or many asteroids, it's all pretty much the same. So swarm intelligence is another major aspect of the space resources industry going forward, because obviously you want to not just send one robot, you want to send as many robots as you can possibly get up at one time. You want to maximise your mass budget, you want to minimise your costs involved per mission, because the single defining cost involved in space mining is how much it costs to get there. And in order to get there, you require a rocket, so we need to go and speak to SpaceX or the Russians, the Japanese, and say, well, we need a lift. So with that lift, I mean, you're all students, the secret is to pile as many people into a taxi as possible in order to minimise the cost per person. Exactly the same application with robots. You want to put as many robots into that lift as possible. And then with fully decentralised robots, ultimately you can have a fully autonomous, infinitely scalable system whereby you will not need human operation in order to operate robots. They will know immediately what to do, which is very exciting. And there's kind of three main operation modes, which is kind of fully autonomous, semi-autonomous, and then remote controlled. And I think kind of having all three of those is extremely important going forward. But what is the applications of a robot, really? Once we've kind of gone past the trivialities of making money and kind of paying the bills, what's the next step? It's having something cheap enough to go and explore the solar system, which is considerably cheaper than anything that NASA, JAXA, Roscosmos, ESA can provide. Private enterprise is very good at finding low-cost solutions to problems, and I would like to think that robotics is one of the areas in which this development can be particularly accelerated, because obviously, closing the name Asteroid Mining Corporation, we're aiming for one thing, but the same technology, its gravity-agnostic capabilities, mean that it can also be applied to lunar and Martian exploration as well. And then, in order to get to the moon, in order to get to Mars, in order to get to those asteroids, make some money. So, inspection techniques, this is all quite boring, so I'll skip through this relatively quickly, that's the wrong way. Infrastructural inspection, we have bridges that need to be inspected, we have tunnels that need to be inspected. At the minute, there is an enormous budget which is predominantly focused on what we call the 4Ds, and that is human inspectors going and doing dull, dirty, distant and dangerous jobs which have quite a high risk to human life. Unmanned aerial vehicles are one alternative, but UAVs can only go so far, can only do kind of such an assessment. Human inspectors can do an assessment, they can get close up, they can kind of look really, really close into the structures, and they're versatile, tactile, can do close up and indoor inspection. They can perform maintenance, but when it comes to a Canary Wharf high rise, you have to either put them on a rope, and rope access technicians are incredibly expensive, or you can build a scaffold, which is again incredibly expensive. And there's a risk to life here as well. The running costs for wages are just enormous. Safety regulations are very restrictive. So, is it the best step going forward? Perhaps not. UAVs can do a very, very quick sweep of an area. If you have a chimney, a UAV can do a very kind of full spectrum analysis, but they can't get close, they can't touch it, most importantly. So that tactile assessment is the most important thing sometimes, because say you have a 100-metre tall chimney and 96 metres up, someone spots a brick which might be a bit loose. If a UAV was to spot a brick that might be loose, at the minute you would have to build a scaffold 96 metres up in order to go and wiggle that brick, just to be able to assess whether or not that brick is in fact loose, and if that brick is loose, you would then need to rectify that problem. Don't have to do that with a robot, send the robot up instead. Much cheaper, much more cost effective, and can reach less accessible areas without that additional infrastructure, which is predominantly the main cost involved. So this is just a very quick capability analysis of where a robot beats humans and UAVs. It's probably quite biased because it's predominantly green, but if anyone would like to suggest anything that we've missed, we'd be more than welcome to take that on board. But robots are very much just one part of the problem of the space resources industry, and that the limiting factor preventing anybody from mining asteroids is just simply data. We just do not have enough data on asteroids, we do not have enough compositional understanding about these objects. They're there, we know where they are. We have kind of orbital data for the most part through the small body database by the Jet Propulsion Lab, but we don't really know what they're made of. And it's that kind of compositional analysis which is really important for the space resources industry, because with that analysis you can start to identify what the real value of an object is in space. Not just the kind of perceived value, but when you actually have kind of solid empirical data, you can start to really estimate and kind of start to ground proof data values as well. And that's really exciting from our part, because that really feeds into the prospecting phase of space resources. And I suppose the question would be, can't you do this from the ground? Can't you just build a big telescope and go and look? It's actually cheaper to do it in space. It costs €10 million in order to build a kind of 2-metre diameter ground-based telescope. And even after that, you're probably looking at about £10,000 a night, or €10,000 a night in kind of operational costs on top. And for the most part, select universities have access to that data, which means that there's a lack of systematic, structured and comprehensive data sets, which really kind of opens up opportunities. So the solution we would suggest would be the asteroid prospectus Asteroid 1, which calculates orbital data, establishes compositions, and identifies candidates for that future asteroid sampling, and that you have something up in a relatively kind of low Earth orbit. It costs about the same, but we are getting considerably more observations per day than you would get on Earth. And the reason for that is quite simple, in that on Earth you have a day and night cycle, so at the best of times you have 12 hours night, 12 hours day. Whereas in space, if you're at a right orbit, you can have 24-hour darkness. You can be constantly looking out into space, and you do not need to worry about a day-night cycle if you choose the right orbit. So we can also look to sort of start populating what we like to call the Space Resources Database, which is a catalogue of solar system resources in the longer term. So this is just a very preliminary specification of the Asteroid prospectus Asteroid 1. In fact, we've had that animation since I think about 2017. So if any of you are aerospace engineers, it's not a very good animation, but it's getting there. It's more like the kind of the crux of everything is that we will be able to do 2 observations per hour. We can reasonably estimate 25U CubeSat, which would be one of the largest CubeSats ever launched. It might require a microsatellite platform bespokely built, but CubeSats are quite cost effective, so if we can use CubeSats we will do. It's an 800-kilometre dun-dusk sun-synchronous orbit, so the sun is always going to be behind our satellite. We are looking out into the solar system, and we're always on the terminator between night and day. So we're always going to be looking out into the solar system and not having sun impact on our observations. We reasonably expect a 5-year mission duration, but with nominal spacecraft functionality, we can extend that to 9 years before it deorbits. And then for that, considering that a 2-metre diameter ground-based telescope costs about €10 million, £8.8 million for 9 years of operational lifespan, and that includes labour, that includes technical costs. That is cheaper than doing it from the ground and more effective. So space technology is absolutely the way forward. So I'm going to take a little bit of a pivot here, and that I'm going to talk about space entrepreneurship, because I'm only a couple of years older than most people in this room. I'm 26, and I've somehow managed to set up a relatively successful asteroid mining business, and I would like to just discuss that for the last couple of minutes of my talk. And that if I had a statement, I would say that you can set up a space company through the University of Edinburgh. If there's anyone in here who's interested in setting up a space business, you can do it. In fact, you could do it tonight. You could go and register a company in Company's House in the next 45 minutes, and it will cost you all of about £13. But once you've set up the business, then you have to be ready to graft, because ultimately there's 2 angles to having a business. One is having an idea, and the second is to be prepared to follow through with that business, because it's hardcore. It takes time. It's taken me, best part of 5 years in order to get a salary out of my own business, in order to kind of, justify my own labour and the market. But it's not impossible. If you do have the desire to do so, then you can do it. And in fact, we've been more than happy to help support the next generation of space businesses developing in the UK. If that's something that anyone would be interested in a bit of mentorship and advice for, please feel free to reach out. So you can do it, but be prepared to work, because if you think your exams are bad, you have no idea how bad business can be. But just to give you kind of brief rundown, if you are to set up your own space business, do 2 things. And in fact, I can really emphasise 2 things. Never say no to journalists is one. It's one of my golden rules of business. Never say no to journalists, because the journalist is going to do a story on you anyway. So half of these stories we were not consulted for, we were not, they never asked us any questions, they just were going to do the story anyway. So if they do ask you, you get to put your own spin on it. If they don't ask you, or you say no, they're going to do the story anyway. So if you do want to set up a business, journalists are your best friends, because they'll bring exposure, bring publicity to you. The other thing is that build out your network of academic contacts, because we are only here by the grace of our academic contacts. We have some very fantastic partners now, across the world, in fact, predominantly based in the UK, some in Holland, some in Japan, but predominantly we are very fortunate to have such strong academic links within the UK, and it's only through that we've been able to kind of sustain the business going forward. So if sort of space entrepreneurship is something you're looking for, I would probably suggest going and getting an academic partner first. Or actually no, set up the business, go hunting for academic partners, raise funding thirdly. And I think if you have a viable business model, and I think that's something which is very important, but if you have a viable business model where you can justifiably expect to make money, even if you're not making money in a minute, if you can justifiably expect to make money, you can ultimately continue in the business, and investors will be interested. They will want to come and talk to you. If they think you're the next big thing, they want to know. And ultimately, they're taking a punt, they're taking a gamble on you being the next big thing. So it's worth kind of bearing that in mind. But I would like to leave you all with one of my favourite quotes, and I think this is kind of very much the fundamental truth which underpins everything about my company and everything about, I would argue, the entire, just about any industry ever. So this is actually from Bill Drummond, who was a musician in the late 80s, early 90s. And there is a fundamental truth that lies at the core of this book. He was obviously writing about, he wrote a book called The Manual, How to Get a Number One the Easy Way, and that he managed to essentially blag a number one hit single in the UK pop charts with some very interesting and entertaining methods, and I highly encourage you to go and have a read at the manual, because it's kind of one of our core texts at Asteroid Mining Corporation. But a truth to me that is far, far more important than getting a number one record or not, I've just added, or mining an asteroid for that matter. That truth is, if you want to do something, really want to do something, don't wait to be asked, don't seek permission, or don't put off until you've passed the exams or saved up enough money, but be prepared to risk complete failure. Because you will, you'll fail and fail and fail again. So don't be afraid of that. Failure is part of human experience. Perhaps not as much KCL, because I imagine you'll probably pass your exams with flying colours, but failure is something which you have to be used to, and particularly in startups. You're going to fail, but you have to learn from that failure. But don't give a damn about whatever anybody thinks, because it's your life and it's your business and it's your engagement with society. So start now, today. Tomorrow's always going to be too late.